Welcome back, everyone. Today, in this explainer, we are firing up our digital holographic simulator to decode the absolute mathematical bedrock of 3D space. I'm talking about vectors. You know, if you've ever told a friend to go 5 blocks down and hang a left, you are actually already speaking the language of vectors. But in physics and engineering, this language is the absolute foundation for understanding motion, forces, literally the fabric of our physical reality. So, strap in, we're going to learn how to navigate and manipulate this digital grid.
Let's take a quick look at a roadmap for today. We'll be hitting 5 key areas: scalars versus vectors, geometric addition, resolving components, unit vectors, and finally, vector multiplication.
All right, let's jump right into part 1, scalars versus vector quantities.
So there's a pretty stark contrast between our two basic data types here. First up, we've got scalars. Think of scalars as just simple, isolated numbers on a dashboard. They have a magnitude, a size, but absolutely zero direction. We're talking temperature, time, mass. Like if it's 40 degrees outside, it's just 40 degrees, right? It doesn't point anywhere. But then we have vectors. These are our glowing neon arrows. They have a magnitude for sure, but crucially, they also have a direction. You can't just say a particle moved 5 meters, you have to specify it moved 5 meters north. Displacement, velocity, acceleration, these are the active directional commands that actually dictate movement in our simulator.
Moving on to section 2, geometric addition and subtraction.
Okay, imagine you're an explorer navigating a massive 3D hedge maze, or maybe you're caught in a total whiteout trying to find your base camp. How on earth do you track your overall movement? Well, we use something called the head-to-tail method. It's super visual. First, you literally just sketch out your initial movement. That's your first vector. Then you take the tail of your second vector and lock it directly onto the head of the first one. You just keep stringing them together, arrow after arrow. And your final net displacement, the vector sum, is basically a brand new arrow drawn straight from your very first starting point all the way to your final stopping point. It completely bypasses the winding path you took and gives you your true net change in position. Pretty neat, right?
Now, if you're worried about messing up the order of your moves, don't be. The commutative law tells us that vector A plus vector B is the exact same thing as vector B plus vector A. And the associative law proves that if you have a whole sequence of moves, it doesn't matter how you group them up. You can add the first 2 together first, or maybe the last 2. Honestly, no matter the sequence of the segments, your final glowing arrow, your net displacement, is going to end up at the exact same coordinates on the grid.
But, here's a question for you. Drawing arrows on paper or visualizing them head to tail is awesome for getting an intuitive feel, but man, it can be incredibly tedious. Is there a faster, mathematically precise way to run these calculations without manually sketching out every single move? Like, can we upgrade this thing to a true algebraic engine?
Let's find out in section 3, resolving vectors into components.
So, resolving a vector basically means breaking it down into its core components. Imagine shining a super bright light straight down onto our glowing vector arrow. The shadow it casts directly onto the x-axis, that's its x component. If you shine a light horizontally, the shadow on the y-axis is its y component. We're essentially just dropping perpendicular lines from the ends of our vectors straight onto the grid axis. This is a total game changer because it allows us to replace one angled, messy diagonal vector with 2 perfectly straight lines that align flawlessly with our coordinate system.
And here is the trigonometric engine powering that whole upgrade. The x component is simply the magnitude of the vector multiplied by the cosine of the angle theta. The y component, that's the magnitude multiplied by the sine of theta. Just keep in mind, theta is the angle measured counterclockwise from the positive x-axis. With just these 2 simple equations, our simulator can effortlessly calculate the exact projections of any vector. It takes those complex diagonal movements and breaks them down into clean, manageable grid steps.
All right, section 4, the unit vector system. So, what exactly is a unit vector? Well, it's a dimensionless vector with a magnitude of exactly 1. It has 0 units, no meters, no seconds, no kilograms. Its sole, exclusive purpose in this universe is literally just to point. Think of it as a pure directional marker on our axes, basically acting as the mathematical scaffolding for everything else we're going to build in the simulator.
And this beautifully elegant equation is the result of that scaffolding. This is exactly how we write a vector in 3D space. We use these special unit vectors, I, j, and k, which, by the way, are usually written with a cute little hat over them. The unit vector I locks right onto the x-axis, j locks onto the y-axis, and k locks onto the z-axis. So when you see a vector written out as axi plus ayj plus azk, you are literally looking at the DNA of that vector. You're seeing exactly how much it moves in the x direction, the y direction, and the z direction, all added together to form the final shape in our neon grid. Now this is exactly why we use this system. Remember that super tedious drawing of arrows head to tail we talked about? Well, once your vectors are in component form, adding them becomes ridiculously easy. You just add them axis by axis. You take all your x components and just add them up. You take all your y components, add them up. Same for the z components. It turns into basic arithmetic. No drawing triangles, no messing around measuring angles on paper. The simulator just combines the matching components and outputs a flawless new net vector.
This brings us to our final stop, Section 5, Vector Multiplication and Rules.
Now, multiplying vectors isn't quite like the ordinary algebra you're used to. The first major distinction we need to make is scaling. If you multiply a vector by a simple scalar, say the number 3, you literally just stretch the vector to be 3 times as long. If you multiply it by -3, it stretches and completely flips its direction. That's just basic scaling. But multiplying a vector by another vector? Oh, that introduces an entirely new reality with completely different rules, and it actually branches into 2 totally different outcomes.
There are 2 entirely distinct ways to multiply vectors. The first is the dot product, also known as the scalar product. It calculates the magnitude of A times the magnitude of B times the cosine of the angle between them. The absolute most crucial thing to take away here is that the dot product outputs a scalar, just a plain old number. It basically tells you how much one vector aligns with another. The second way is the cross product, or vector product. This one uses the sine of the angle, but crucially, it outputs a brand new physical vector out there in space.
Let's look a little closer at that cross product. If it generates a brand new vector, where's that vector actually point? Well, it points completely perpendicular to the plane formed by the original 2 vectors. So, if your first 2 vectors are lying flat on your desk, the cross product vector is either going to shoot straight up out of the desk or straight down through the floor. It literally generates a brand new dimension of direction in our 3D hologram. To figure out whether it shoots up or down, we actually use physical space. Seriously, I want you to literally raise your physical right hand right now to interface with the simulation. We're going to use the right-hand rule. First, point your fingers perfectly straight along the first vector, vector A. Next, imagine sweeping or curling your fingers through the smallest angle toward vector B. Finally, look at your outstretched thumb. Wherever your thumb is pointing, that is the exact perpendicular direction of your new cross-product vector, vector C.
But I've got a major warning for you here. Remember how we said vector addition doesn't care about order? Well, in cross multiplication, order is incredibly critical. The commutative rule completely fails here. A cross B is absolutely not the same as B cross A. If you reverse the order, like if you sweep from B into A, your thumb is going to point in the exact opposite direction. Reversing the vectors literally flips the entire outcome upside down, introducing a negative sign. We've covered some incredible ground today, from the basic arrows of displacement all the way to the multidimensional generation of the cross product. But I want to leave you with a somewhat provocative thought as we power down this module. Vectors describe the absolute physical reality of our universe, but we measure them using artificial coordinate grids. So if vectors define this absolute reality, what happens to their x, y, and z components if the observer's coordinate grid itself begins to rotate? Does the vector actually change, or just our perspective of it? Think about that puzzle as it relates to advanced physics and relativity. I have a feeling it'll leave you hungry to boot up our next explainer.